Welcome back to chapter 1.3, projection at an angle of our grade 12 physics. So we'll talk a little bit more about some of the work we've been doing about projectile motion and take it a little bit step further and use some of the formulas a bit more. You can pause the video and have a look at these questions, look up the answers if you'd like, see what you can discover. Alright, so what's the point of this lesson? We're going to investigate the horizontal and vertical components of a velocity vector, study how the horizontal and vertical components are dealt with independently, and we'll accurately resolve the motion of objects in two dimensions. Okay, when we project an object through the air at an angle, we often refer to it as a parabola. Okay, it's an object moving through an arc through the air. And although it's not perfect when you compare it to a parabola, but it's a very, very good approximation of the motion of that curved object through the air. So when we look at our formulas such as this bloke here, the thing that really makes a difference, particularly as the displacement varies, is the time it's actually traveling. The longer the object's got to travel through the air, obviously the more the displacement will be. And that's why we've said it's a function of time squared. The horizontal displacement gets back to our speed, distance, time, a formula that we spoke about a lesson or two ago. Varies once again according to time. The displacement's always changing over time because the more time an object's got to move, the more distance it's going to move. We discussed this question last time. The horizontal displacement is often called the range. It's the distance it travels horizontally across the ground. So we're going to look at these three scenarios that are down the bottom here. We're going to look at an object launching and landing at the same height, landing lower than its original height, and landing higher than its original height. These things look a little bit complicated when you look at the questions, but the reality is it's not that much. Once you break it down, it's not actually that difficult. And if you think about a little bubble over the side here, what can we determine? If an object lands at the same height, displacement in the horizontal direction should be 0. G is never going to change. If the object lands lower than the original height, then the displacement in the x direction will still be there. The displacement in the y direction is going to be a negative value, and so on. Okay, so I encourage you to stop and think about those variables before we go too much further. Okay, case 1, landing at the same height as launch. Here's where our object's launched from, here's where it lands. And when we say at the same height, we mean on the y-axis, it is the same height. Obviously the x-axis is different, but in the y-axis, it's going to be still returning back to 0 again. What do we notice in terms of speed? The impact speed and the launch speed are the same. The velocity, it's the same magnitude, but in a different direction. As in the initial velocity up is the same as the final velocity, but down. Okay, hence we've written it there mathematically. Here's another example of the same sort of thing. A few more examples. In that top one there, you can see that the horizontal velocity doesn't change as it moves, but the vertical one, the initial one, and the final one are the same, but in opposite directions. And there's this point at the top here where the velocity in the vertical direction is 0. Right, let's look at an example. A bullet's fired from a rifle at 200 meters per second, kind of fast, at an angle of 40 degrees to the ground. Okay, so we're going up at 40 degrees at 200 meters per second. We can go back to the resolving the vectors like we did back at the start, or we can actually look at the formulas that we had that we looked at a lesson or two ago. And I'll come to that when we look at that solution. So what are we going to find out? Vertical and horizontal components of the velocity, initial velocity, the maximum height that the bullet reaches, the time of the flight, and the horizontal range, or the displacement on the x-axis. So let's have a look at the answer. as I said, we have initial velocity, the angle that it's released at, the gravity doesn't change, upward is positive. So firstly, we're going to look at the vertical direction. This formula here we looked at a little while ago. U in the y direction equals u sine theta. And we know what these numbers are. He goes in here, he goes in here. Remember that equation because it'll make your life easier to work it out. And same with horizontal over there. And once you plug the numbers in, you simply plug it into your calculator and do the maths, and it all comes out in the wash. You have your horizontal and vertical velocities initially. That's your answer to question A. All right, B, the maximum height. All right, so at maximum height, the vertical velocity is 0. So once again, write down what you know, look at your equations, pick the correct one. And that's this guy here, because we have this value, we have this value, we have that value. That's what we're finding out there. This gets rearranged, so the S is on its own. Plug your numbers in on the next line, and it all comes out in the wash. The vertical height that the bullet travels is 844 meters. And that's 3 significant figures. Okay, so the time of the flight can be calculated 3 ways. We have the bullet that starts at a point, flies through the air, and hits the ground again. We can calculate the time it takes for the bullet to get from that start point to the top, as in how long does it take for the vertical velocity to get to 0. Once we've worked out that time, we double it. And that's kind of like saying that the bullet has gone up and come back down again, because we're only looking at the vertical direction. From here to here, and double that time. And that's how we get the time of the flight. Or in the second one here, we can look at the time taken until the final velocity in the vertical direction is equal and opposite to the initial velocity. Take the velocity here at the start. When it's the negative value of that at the end, that time is how long it travels. Or in the last one, when does the vertical displacement get to 0 again? So as the bullet goes up through the air, the vertical displacement changes. When the vertical displacement gets back to 0, that's its time in the air. All right, so there's 3 different ways we've done it. Let's have a look. V equals U plus GT. We know V and U because in the first scenario, this is the first method, time to reach maximum height, where the final velocity is 0. That's this point here, where the final velocity is 0. So that would be 0 for him. The initial one is 129 meters per second in the vertical direction. This formula was rearranged to that. Plug the numbers in to get that, and it all comes out in the wash. That's the time to get to the top of the trajectory, 13.2 seconds, which you would double to get the total time in the air. Method 2, we've got the same scenario, except what we're doing here is we want the final velocity to be the inverse of the initial velocity. As in, if it takes off vertically with 129 meters per second, it's going to land with 129 meters per second. It will be the negative value. It's done the same way, 26.24 seconds, which is what we had before. And the last one, determine the time until the vertical displacement is 0 again. So we've got a different formula here. S is equal to ut plus a half gt squared. The displacement is going to be 0. I know what my initial velocity is, 128. T is what I'm working out. And a half times 9.8 is that guy there. And there's another t squared we're working out. When you rearrange this, what we've done is we've taken this last term and put it on the other side of the equation over here. And we divide both sides by t to eliminate the t squared. And we end up with 4.9t equals 128.6. Divide both sides by 4.9, 26.24 seconds. That's the total time of flight. 3 different ways we did that. Okay to go back and revise that one again because it is a little bit complicated conceptually. And horizontal range, we've got a formula for that which we've used before. S in the x direction equals u times t. We know what u is, we know what t is, we plug the numbers in, and we get an answer, 4,020 meters. All right, case 2, landing lower height than at launch. There's a few pictures here of that I found, and then I thought I'd put a few pictures of Evel Knievel in some of his amazing motorbike jumps and so on. He's worth looking up well before our time. Now, if we land at a lower height than when we launch at, think about our question in the middle here. The impact speed should be higher. The impact velocity should be higher because if an object starts at a certain point, if Evel Knievel starts his motorbike jump here and he lands at a lower point than where he started here and lands down here, he has time to accelerate that extra distance down, hence his impact velocity should be higher. All right, and that will change the angle a bit. Here's an example. Cannon's fired from the edge of a cliff, 60 meters above the sea level. The initial velocity of the cannonball is 88.3 meters a second and fired up at 34.5 degrees to the horizontal. These questions look complicated, but go back to what I told you before. Write down what you know, look at your list of formula, and you should be able to pick one that works to find the unknown that you're after. We need to find the time the ball's in the air, the impact velocity, and the horizontal distance away from the cliff, as in how far, what is the range that it travelled. All right, back to our formulas. Vertical component of the initial velocity. Got our formula that we used before. Plug our numbers in. We know it starts at 88.3 meters a second and at 34.5 degrees. The initial velocity in the y direction is 50 meters a second up. We do the same with the horizontal component and we get 72 meters a second across. The final vertical displacement is 60 meters because it told us that the cliff was 60 meters high. Gravity doesn't change. Okay. All right. So notice the little point down the bottom here. We're calculating the vertical velocity, the initial vertical velocity first, so we can avoid using quadratics. All right. Now, same deal. Find our equations and plug them in. So we want to find the final velocity in the vertical direction. There's our formula. We've got our numbers we plug in and gives us 60 meters a second is the final velocity. And you can see we've got that down here in our diagram there. All right. Now, what do we do with that? We've got our next equation here, which has got t in it. Notice the first equation we used because it had v, u, g, and s. We're ultimately finding t, but we use that equation to find the final velocity to avoid the t squareds and the quadratics. So hence we did that one first to get the final velocity. We use this next equation here to then find t. Rearrange it. The time is 11.3 seconds. It's worth pausing and looking at where I put the numbers in. We knew what v was because we calculated it up here. We know what u is because we calculated it before. And g doesn't change. Right, the impact velocity calculated by the vector addition is the next step. So what have we got? We've got this final velocity in the x direction. We didn't need to do anything with that because the velocity in the x direction doesn't change. We had to calculate this one because the object is landing, it's starting at a certain height and landing lower than what it was. At this point here, its velocity is the same as what it was here. So it has this extra time for the acceleration to take effect. That's why we had to do all of this bit here. Right, the rest of this bit here, you can just have a look at the stuff on the screen there. It's the stuff we've done before. We want to combine our two vectors, do the vector addition here. There's two things we've got to do. We do the Pythagoras to get the magnitude, we do the trigonometry to get the direction or the angle. And that's what's happened here. We've got our final velocity there. which we did using Pythagoras, and we did our trigonometry to get 39.8 degrees. All right, part C, horizontal distance. Once again, we've got our formula, which is just the v times the t. How fast are we going? How long have we got to travel? Gives us how far we go. Plug the numbers in. It's the same as the one we've done before. All right, case 3, landing at a higher than launch height. So the example on the ball here, we start there, we end up there. What's the difference? What's the difference that this makes? What can we say about our impact speed? It's going to be lower. Our impact velocity is going to be less, and the angle once again is going to change. So at time 0, the displacement in the y dimension is 0 meters. That's what that says. The displacement at the end is going to be a little bit higher, and you can see we're starting off here at 1.9 meters. We end at 3.1. That is displacement in the y direction. 1.2 meters. Simple maths will give you that one. Displacement in the x direction, from where we start to where we finish, you simply read it off the diagram. 4 meters. The angle, all right, when we work out the angle, that's a little bit different. We start off our initial angle at 60 degrees upwards. Working out this angle is a different issue that we're not looking at right now. And gravity is always negative 9.8 because it doesn't change. Righto. What can we say about velocity in the x direction compared to the y direction? It's the same because the y and the x are looked at independently. There is no acceleration or no unbalanced force in the x direction. So the final and initial is the same. The impact velocity and the launch velocity, they should also be different. At this point at the top of its trajectory, the vertical speed or velocity is 0, so it only has to accelerate down to there. If it accelerated back to where it started, they would be the same, but because it has less time to accelerate, you would expect the velocity here at the end to be less. Once again, check out some of these check your learning questions to work your way through this. There's a few extension things here you can have a look at. And complementary angles, one thing we should discuss. You may refer from geometry back in grade 7 or 8. Complementary angles add up to 90 degrees. They don't just say nice things to each other. But what it means is that the result of a launch angle of 75 degrees and 15 degrees will give you the same sort of range. They're complementary to each other. This example will basically go through that and prove that. Okay, we have a vase ball struck at 20 meters a second, pretty fast, 60 and 30 degrees. And we know that 60 plus 30 equals 90 degrees, so they're complementary angles. So we'd expect similar results here. Time of the flight and the horizontal range. How do we work those out? Calculate the components. So we've got the vertical component there and the horizontal component there. Its initial speed is 17.3 vertically and 10 meters a second horizontally. So that should stay the same. Time of flight. We've got this little bloke here, which once again, write down your formulas and you should work it out. This is the one with time in it as a variable, so you know to use this one. Plug your numbers in, you know what U is, you know what G is. And what do we get? This little bit here. And we continue with our mathematics down here. And I encourage you to pause the recording and have a look at that. As we do, this is just the algebra of it all. We worked out, when we sorted out the algebra, 3.5 seconds. That was for the 60 degree angle. For the 30 degree angle, we do the same thing. And we saw that the time of flight is a lot less. Okay. Pause the video, look through those things and work out where I put the numbers, where they came from. These formulas are simply the same. Look at where the numbers came from and where we stuck them in. That's how we work out the time of flight. You would expect that if a ball goes up at 60 degrees like that, and at 30 degrees, the 60 degree one has longer in flight. So, calculate the range. What that tells us is the displacement in the y dimension is 0. So how long do we get back to the starting height? S is equal to u times t for 60 degrees and 30 degrees. Notice that the angle is not coming into it. It's just the initial speed times the time. Okay? And they're all 35 meters. And that's what we expect out of our complementary angles. All right, there's a mandatory pack there. Have a look at that video there. It'll talk you through it a little bit from the author of the book that I've been basing this on. We did do our learning intentions today. It's been a bit of a long video. Thanks for getting this. So have a look at the case study 1.3. Have a look at Check Your Learning 1.3 and your time to do the chapter review. All right, thanks for coming.